Hello. Thank you for your interest for this presentation. We will develop a really true three-dimensional representation of a Mandelbrot function. We will analyze the values of Mandelbrot's iterative function. First, let us remember how Mandelbrot's iterative function works. The definition is as follows. In this presentation we call the Mandelbrot set the inner area. All other points we call the outer area. Based on this definitions, a typical two-dimensional representation may look like this. The main hall, the main gate, the inner area, the outer area, and the satellites. Two-dimensional representations are normally obtained using the concept of escape values. The definition is as follows. For each possible escape value, all corresponding points are painted with the same color. For each escape value is used a different color. Here we have some examples of escape value layers. As the inner area never reaches a static structure, at each iteration step it is different. Usually this area is painted with only one uniform color. Nevertheless, the inner area is a highly interesting area, especially for its high dynamic and chaotic behavior which can be observed only using video sequences as we will show in advance. We also can appreciate that the outer area shows a very strong three-dimensional structure. It looks like the trunks of trees in a very dense forest. Following examples show that this aspect can be appreciated up to extremely high zoom levels. Now we start our three-dimensional investigations. The first step is to analyze the three-dimensional structure of the outer area which we have seen before. To do this, we apply a detailed geometric analysis to the value set of the function. This analysis permits us to get out all border lines between escape value layers, as nearly smooth and differentiable mathematical curves. Look at this image. It's based only and exclusively on the extracted borderline curves. Now we can differentiate these curves and calculate the normal vectors at all points of the border lines. These normal vectors enable us later to make an acceptable shadow rendering for our constructed three-dimensional model. Here are some examples of borderline curves and normal vectors. Geometric analysis gives us not only differentiable border lines. Also we get what we call isolated points, defined as pixels which does not have any neighbor within the same escape value layer. Isolated points do not contain any information about the geometric structure of the Mandelbrot function, they are only just at the zoom level we are. Nevertheless, sometimes we will use them as decorative elements. Finally, the geometric analysis gives us also information about the shortest ways from any inner border point of an escape value layer to the outer borderline of the same layer. We use these information sometimes to make a more amazing rendering of three-dimensional as well as two-dimensional models. Look at the following images to see how the shortest way information works and how it can be used in the rendering process. Shortest ways. Putting all together, now we can obtain a lot of really three-dimensional images. For example, the frozen main gate with a magnification factor 11. It's worth to mention that the frozen main gate image and all the following images are only based on the geometric information, which we have extracted from the Mandelbrot function. without using any smoothing algorithm or other sophisticated and artistic tricks. The only informations which does not come directly from the Mandelbrot function are the color assignments as well as the pixel height assignments for the escape value layers. Before showing more images, we will use the base image to indicate the points from where these images had been taken. The frozen main gate which we saw just before. A cold winter day which will be the next one to see. Then the Sky City. And the Julia Palace. And the Avatar Forest. The Highway Junction. The wireframe model. And finally the hidden lake, the natural Velcro system, and the fighting monsters. We also indicate the point where the evolution video of the Tornado Valley has been taken. We will see this video in the following section about the evolution of the Mandelbrot surface. A cold winter day, with a magnification factor of 33. The Sky City, with a magnification factor of nearly 90 billion. The Julia Palace, with a magnification factor of 20 billion. The Avatar Forest, with a magnification factor of 20,000. The Highway Junction, with a magnification factor of 111. The wireframe model, with a magnification factor of 4. The hidden lake, with a magnification factor greater than 28 million. The natural Velcro system, with a magnification factor greater than 555,000. The fighting monsters, with a magnification factor greater than 555,000. Now we arrive at the second step of our investigation. Make visible the dynamic and chaotic three-dimensional structure of the inner area. We built a three-dimensional model for points of the inner area using as height values the following distances. As we just know, for points of the outer area these height values tend very quickly to infinite. But whilst the values keep finite, we can use them to analyze also the outer area with that concept of height values. In the following pages we show a sequence of images of the three-dimensional surface built with this height value concept. For each iteration step we will show two images. One image viewing the surface from above and another one viewing it from the side. Step 1. Accept height values 0. The model is painted altering between dark and light color values. Height value 0, which is the ground level, is painted with color yellow. Step 2. Step 3. Step 4. The surface just starts to shrink towards the commonly known Mandelbrot figure. Step 5. Height values of the outer area are just so high that we stop the altering of dark and light color values and we paint these points uniformly with light blue color. Step 6. Step 7. Step 8. Step 9. Step 10. Step 11. The height values of the outer area points are just not computable as being higher than the maximum value of double precision numbers. Corresponding points are painted with color black. Step 12. Step 13. The fluttering of the satellites is just running at full swing. Step 14. Step 15. The evolution continues, each iteration step making the border between outer area and inner area more sharper. What does not change is the fluttering of the satellites, and it seems to be so forever, whatever might be the reached iteration step. And now, after we have seen the global evolution of the Mandelbrot surface, the following video gives us a detailed show of this evolution in the area of the Tornado Valley. The video will be played several times. This way it's more easy to see what happens in the Tornado Valley. For example, it's quite amazing how in this zone the outer area wins step by step the game against the inner area. But the inner area strikes back strong in order to bring back under his control the escaped tornadoes. The last step of our presentation will show an evolution video which combines all together, the inner area as well as the outer area and the Mandelbrot surface. The video will be played also several times. This gives us the chance to understand the growing of the outer area forest, as well as the dynamic and chaotic behavior of the inner area. At the end of the video we will show how a step-by-step decreasing of the pixel height assignments degenerates the three-dimensional model to a flat two-dimensional model.